Therefore, there has to be different assessments like the process assessment. There has to be environmental assessment. That means how effective is the system's environment and how difficult is it to maintain, or how expensive it is to maintain the system in that particular environment. Is the environment still available, or if the environment changes, that means that operating system becomes unsupported by a particular organization, or a particular hardware system is discontinued, then what do you do in that case? How would you manage to keep that system running? So these are some of the challenges. So that means that environmental assessment has to be done. So in that case, if that happens, obviously there is no other alternative available except to replace the system, or you might have to find some sort of emulation environment to support that system. So you have to get certain emulators, which are called as emulators, like say for example a certain system would only run on an old Windows system, and since that old Windows environment, operating system environment, or that operating system is being replaced by the new version. Now just to support that legacy system, you might have to run emulating software that emulates that old, say for example DOS environment, and that DOS emulator will allow you to still use that system, which is dependent on a particular old operating system environment. So that assessment has to be done as well. And is it is an alternative available? Is there an emulator available which can support that legacy system, or it has to be changed? Application assessment has to be done. That means the quality of the application, the quality of that particular software application has to be assessed as well, to understand how the system stands altogether. So when we look at the business process, obviously we are looking at certain factors, and one of them is the process model that it supports. If it supports a particular process model, so that process model obviously is there a defined process model that is followed and that is still supported by that legacy system? Do different parts of organization use different processes for the same function, which means there is some degree of redundancy, and that affects the system. How the processes have been adapted or changed, during the progress and during the different requirements that they come and arise as different business rules changes. Do the processes have been adapted? Does the system support new processes? These are some of the challenges. These are some of the things that would determine in terms of business application of that software. The relationship between business processes. So basically, what are different relationships that software has with other business processes? So we are talking about how this would interfere with some other business processes. That means the interconnectivity between a particular legacy software with other business softwares, or with other business processes that are being implemented with some other business softwares. So these are some of the challenges. So in the process of looking at whether a particular legacy application must be supported, we have to look at all these factors. And a typical example of that is a travel ordering system. This example is relevant because in a typical office environment, you have a console-based application, or rather a front-end system, which is being used to process travel orders. But then you see that a lot of customers are now using web-based or an online system to book their travel tickets. So in that case, that travel ordering system that you have as a enterprise system or as a in-house system, how relevant and useful that is. If we look at the environmental assessment, environmental factors, then we have to look at certain things, and these factors are the supplier stability. The supplier of that software, is it still supporting that software, which means is the supplier financially stable or giving you the support and giving you the confidence to carry on using that software. So that is the supplier stability, which means are you still getting a technical support from that supplier to maintain that software. That's one of the questions. If you are, then you may continue. If you don't, probably you might have to look for a change. The failure rate, every old software, legacy software would definitely have a certain amount of bugs and failures because of continuous change and adaptations that it has gone through during its life cycle. So because of that, probably a legacy system do sometimes are prone to certain failures as well. So depending on, and plus if they run on old hardware, if they are running on old hardware systems, probably they have a higher probability of facing failures or hardware crashes, and that also has to be looked upon. So if the system is often falling to crashes and it restarts, the server quite frequently takes a restart, either it crashes or it hangs, and that obviously has to be looked at. Age, how old is the hardware and software? So basically, as the age increases, the vulnerability of your hardware and software crashing also increases, and that has to be looked upon. The performance, okay, it might be okay, the software is still working, but how is it performing? So is the performance of the system adequate? That means if the load on the system increases, the number of users increases, the number of connection increases, or the number of requests increases, how does it perform under heavy stressful environment? So that is also one of the parameters to the system needs change or not. The other environmental factors such as support requirement, do you have a local support, which means we are talking about technical support to the system, whether it is available or not. Maintenance costs, what are the hardware and software maintenance costs and support maintenance costs. One of the factors could also be the licensing costs of that software. So you have to buy licenses and you have to pay the license fees as well. So definitely old systems would have a higher maintenance cost than the new system. That is for sure, because they run on old hardware. Probably the maintenance engineers or the maintenance experts are also very few, scarcely available, so the charges are high. So that definitely is one of the case. The software licensing cost is another factor which you have to look at. Other factor is interoperability. So many of the old systems do face that problem of interfacing with other systems, because obviously as the environment change, as the systems and different server environments change and the operating system environments change, we'll see that certain software would be sometimes not operating to its full capacity, or maybe not even functioning properly. So the point here is that the compilers are they compatible with the current versions of operating system or not? Can they run on your latest operating system environments, whether it is your Microsoft Windows operating system or you're using the Unix systems probably? So is the support available? Are they still operating? Are they what do you call that, the backward compatibility, is it there or not? So you have to look at certain factors in that context as well. So if a system is having a backward compatibility, which means it can run on older systems, plus it can also run, or a particular new operating system can actually handle certain older legacy systems as well. So that's one of the things that happens. Okay, at the application assessment level, what are the factors that are required? Obviously, at the application level, as we have seen, that as the business process change, the software has to be changed, adapted and modified accordingly. So some of these legacy systems actually are written in very old languages, so their source code has to be changed, and obviously you have to find people who can work with those source codes. They can work with legacy computer languages like Fortran or COBOL, or the earlier versions of C. And at times the challenge is to find the experts for that. Sorry. So we have to look at whether you can find the experts that can be hired to make changes to the system, to the source code, and do we have enough of those resources available to work with certain legacy systems? Do we have experts on those old languages sometimes, which is very difficult to find, and as a result of that, it's very difficult to maintain some of these legacy systems. Other drawback that some of the systems suffer is with documentation. So the old systems obviously never gave much of stress on documentation. They obviously were programmed, and the programmer used their own imagination, didn't follow a thorough documentation or commenting protocol, and as a result of that, these systems don't come with a very clear, well laid out documentation. So this makes it very difficult for any new system programmer, any new maintenance engineer to come and work with this system and change the system as per the requirements of the business. So these documentations at times are missing, or they are incomplete, or they are inconsistent, and these are some of the challenges that we normally see. The other one is the data. So do this system have a data model? Many of the old legacy systems either used flat files, which were actually simply files in which these data were written, plain old files in which the data was written and was fetched. So that resulted into a lot of redundancy. That means a lot of data was duplicated because it wasn't very well implemented on RDBMS system, relational database management system, which obviously is a much more refined system in terms of data maintenance and in terms of reducing redundancy of data. Some of these systems work with old versions of database management systems. So basically they are working with DBMS systems, not really RDBMS systems. That means that relational model is not there, or relational model is missing. So that also is one of the challenges, and some of the systems suffer from these drawbacks, and that's why it could be a factor of assessment whether the system needs to be changed or scrapped or replaced. Performance. Many of these systems, as I said, may be not very good in terms of performance, because some of these systems are not scalable, which means that probably these systems were designed to handle a set number of users. And as the business increase, the business requirement increase, the number of users also increase, and that puts a toll on the performance. So is the system or the application performing adequately in a particular set of requirements or not? So that basically is also a very important parameter for deciding whether a system So do we have the test data when the system is tested? As I mentioned about regression tests, so if the regression tests are carried out, is it documented properly that the regression tests were conducted? What was the output of those regression tests, whether it was successful or it failed? So these are some of the test data we are looking at, and that has to be considered as well. The personal skills are the skill set that is available to maintain that application. Are those people available who can basically make modifications to the system or reprogram certain components of that system, probably rewrite or refactor some of those existing we also have to look at other factors, which is collecting quantitative data to understand and to measure, to quantify the quality of the application system. And what are the factors that would be considered while you are measuring the quality of the system? On a broader sense, you would be looking at how many system change requests have been generated. So system change requests, if you have higher system change requests, that means that the quality is lower. How many system interfaces are being used, different user interfaces that are being used by the system? If there are more system interfaces, more interfaces of that system, then probably there are more inconsistencies and more redundancies. So that's also one of the measures. The volume of the data that is used by the system, that means the number of files that are associated with it, the size of database that is associated with it. So as the system becomes older, you will see that probably the number of files and the size of database it is associated with also grows. So do the inconsistencies and the errors in a system. So if a system is used more, has been used over historically a very long period of time, then you would see that yes, there will be a huge database, there will be more inconsistencies and errors in that data as well. And cleaning the old data is very, very tedious and very expensive and time consuming. So when we look at maintenance, and of course as we have seen that every software goes through the maintenance. So we see that certain things are to be considered. So when you are modifying the program, you would see that there will be new versions of that software that are created. So as we discussed about different reasons for which a system maintenance is done, and obviously the reason is that the business requirement changes and the software processes, the business process is changing, and as a matter of reaction to that, or for the software to remain relevant, you have to make changes to the software as well. So when you are changing a custom software, so we'll see that normally certain generic software products now become more specialized, or they rather become more adapted to a particular business environment. So generally that maintenance is a natural process, it's a fundamental process to any system. But we would also see that these maintenance normally is done in terms of sometimes adding new functionality, sometimes rewriting the software to optimize it, to remove certain errors or bugs in that software, sometimes to make it more efficient, or rather to improve the structure of the programming so it can be supported well by the new set of programmers, or probably rewritten in a new language sometimes, so it is further supported by existing programmers. So maintenance does not really involve major changes of the system architecture, but it does keep on changing the system structure. It would keep on changing sometimes adding new functionality to the same software, or it probably would be optimizing the existing software to some extent. So changes are implemented by modifying existing components and adding new components to the system, which means that the system obviously keeps on continuously being changed and adapted to the new requirement. Okay, what normally happens in terms of maintenance? So one is something called fault repairs. So fault repairs basically is fixing the bugs and the vulnerabilities in the system. The other one is environmental adaptation, which obviously means that changing the operating system environment, or changing the hardware. So these are environmental adaptations which are done. So in order to make the system still working, you would require that it needs to be modified to run on a particular new version of operating system, or in order to still keep it compatible and running on a particular set of servers which have been upgraded now. So that means the hardware and the operating system. So these two are the two major drivers that basically also call for a system maintenance, in order to make the system adaptable to the new hardware, and in order to make it functional in a new version of operating system. Probably a system needs to change, and this is part of the system maintenance. The other one is the additional of functionality, the functionality addition or modification. So either you are adding a new functionality to it, or you are modifying the existing functionality to suit present business requirements. It is done. If you look at this graph, we see that most of the maintenance effort actually goes into adding new functionality to the system, which is 58%. Then the next is the fault repairs. That means removing any bugs and errors from the system, which obviously are exposed as the system is being used in the real world environment, is being deployed in the real world business environment, and then you figure out there are some bugs, there are some faults which has to be repaired. So 24% of that effort goes into fault repairs, and 19% goes into the environmental adaptation. So this is where your operating system has changed, or probably your hardwares have changed, your servers have been upgraded, and that is the reason why you have to carry on to the maintenance of the software. It has been seen that sometimes the maintenance costs are twice that of development cost, and this happens because once the system is put to the real test into a real business environment, that is when you will see that certain requirements don't fit. There are certain bugs or errors in the system, or probably there are some performance issues. The system is not performing adequately on a particular environment, and that is where the system has to change. So we'll see that normally the maintenance costs are twice more than the development cost. So, and this is affected by both by technical and non-technical factors. So when we say technical, we are talking about basically the change in the technical environment, which is normally the hardware and the software environment, operating system environment. And non-technical factors would be some other factors in terms of adapting that software to new legislation, adapting it to some new or some modification in the business process, probably changing the business strategy. A business strategy changes because of competitors move, and as a result of that you have to modify your own system. So these are some of the reasons why probably you'll see that maintenance kicks in, and that obviously inculcates into the maintenance cost of the software. So as the software is maintained, you'll see that the maintenance cost will keep on increasing. The other thing that happens is that maintenance corrupts the software structure. So as the maintenance, obviously, these are some ad hoc changes that happen into the software. So you're going to go to a particular module and change from some piece of code over there. So probably that change may not lead to, that change may affect the software adversely in terms of creating inconsistencies within the software. So software structure actually gets corrupted. And then as it is done more and more, as the changes are carried out more and more, you'll see that it basically degrades or corrupts the software structure, and it keep adding to the issues of maintenance of the software. So the maintenance become further more difficult as the software keeps on changing, and the structure, the basic structure and the flow of the program gets disturbed by frequent changes into the software. Aging software, obviously the software which is getting old will definitely suffer from high support costs, because it's very difficult to find programmers and experts for those technologies, like old programming languages, as I mentioned about your COBOLs and Fortrons and the C and some other languages that have been used earlier in software development, and even the compilers are hard to find for those old softwares. Okay, we also find that it is expensive to add new features to an existing system, then adding them at the time of development. So at the time of development, adding a new system, adding a new feature to the system is easy compared to adding it after the deployment, because that makes it more expensive, because it also breaks the whole the structure of the program. Plus it can lead to a lot of errors and bugs and inconsistencies in the software. So that is what happens when that's why we keep on, there's always a stress on early testing of a software, because we normally see that early testing of a software or early removal of bugs would actually lead to low cost incurred in the software development. Whereas if these changes or adjustments are made in the later part of the software development, then obviously it becomes more costly affair, because there's a whole large piece of code that has to be changed. Now the same thing becomes true after the deployment, because now the software is all programmed and it's been done, and now you're going to go and make some changes, some adaptations to the software, which obviously will lead to a consistent back trail of how it is connected with other components, and that actually leads to a more expensive exercise of software maintenance. So that's what we see, that it is more expensive to add new features during maintenance than in the development phase of the system. One of the reasons why these costs are expensive is because there's a new team which is called upon to make these changes, which doesn't understand the system. So first they have to spend time to study the system, to learn about its functionalities, and after that they would obviously be able to make some changes. So separating maintenance and development means there is no incentive for the development team to write maintainable software. Yeah, that is true, because the guys who are in the development team are only worried about their deadlines and their delivery dates, so they are rushing to deliver the system, and obviously they don't have a incentive to, or rather they know that they are not going to be involved in any further maintenance of the system. So if that is the case, they are not worried about how easy or difficult it will be to maintain that software later on. So their job is done, and somebody else will have to go and clean up the dirt if they have done some lousy programming, they haven't done a proper documentation, they haven't put proper comments wherever it is needed, and then definitely it makes for the maintenance team to maintain that software, because it becomes a nightmare. Some programmers, it has been seen, that have done that deliberately because they wanted to make somebody else's life difficult, and they sometimes deliberately don't follow the good programming practice of putting up the variable names that are relevant, understandable, and it has been seen that some of them actually have gone so far that they use completely non-relevant variable names. They don't put any documentation, and that makes it very difficult for the maintenance team to maintain it. And not to say that some of them notorious ones actually do that deliberately, intentionally, to make other people's life difficult, although it's not a good programming protocol or good programming standard practice. So that's something that happens in the programming world. So program maintenance work is not a very popular one, so that means that you don't find very experienced people sometimes doing the maintenance work, because maintenance is actually sometimes seen as cleaning up somebody else's dirt, or kind of like a low priority work, thinking that it's just to do some cleanups, do some few changes here and there. It's not taken very seriously. So that definitely also creates its own problems, because inexperienced people would obviously lead to further degradation in the quality of maintenance of that software. So as the program age, the structures degrade, it becomes more and more hard to maintain. And as I said, if you are not using experienced maintenance team, they would further speed up the process of destroying or degrading the structure of the program, and would sometimes lead to more bugs into the system. Okay, maintenance prediction is an effort which is made in order to understand, or in order to predict the number of changes that a software would require during its life cycle. At times it needs to identifying the parts of a system that are most likely to be changed, and also determining the cost of those changes. So to understand or to predict the number of changes that a software will undergo, and also predicting the maintenance cost of the system over a specific time period, so you can set up a maintenance budget for that software. So that would require certain factors, and it basically depends on understanding the relationship of that software with the external environment. And it has been seen, if a system has a very complex relationship with its external environment, the more complex is the relationship, more changes it will require in during course of time. So certain factors that actually helps to evaluate the relationship between the system environment and the system itself, and also becomes the determining factors for amount of cost that will be involved in software maintenance, involves the number of complexity of system interfaces. So basically we are looking at how many system interfaces exist. That means at how many times that software has to interact with the external environment. There is something called a cyclomatic complexity, which is a software metric for any software, which actually tries to quantify quantitatively, it tries to measure through a formula how complex a system is. So cyclomatic complexity is used in software testing to figure out how many different independent paths exist for a particular program or for a particular software, and you have to design your test accordingly to cover up all the independent paths. So basically, if a software is more complex, definitely there's a chance that it will be asking for more maintenance, and it will be eventually resulting into more maintenance cost. So you have to budget that cost, and you have to keep that as one of the factors in terms of deciding about how and how much expenses would be incurred into maintaining that particular software. So the maintenance costs depend upon the changes and the cost, which depends on the maintainability of the software. So you can see that even implementing these changes would result in degrading of the system, and obviously would result into increasing of maintenance costs when the system which we're going to see. So we have to look at what parts of the system are most likely to be affected by the change requests, how many change requests, and which parts of the system gets affected by the change request. That's one of the parameters to foresee what changes the system will require. So how many change requests and how many and which parts basically are to be more affected by that change request. So if a request come in a particular module, that has to be documented that how many change requests came for that particular module. So that becomes one of the indicators. There are certain parts of the system which will be more expensive to maintain. So you also have to look at which part of the system would be more expensive to maintain. So this is to predict the maintainability of the system, to predict the number of the system changes, to predict the maintenance costs, you have to figure out these parameters. For the cost, you have to look at what will be the lifetime maintenance cost, as I said, and that will depend on the complexity or the cyclomatic complexity, as I mentioned. Let's call it as CC, cyclomatic complexity of the system. So that would determine the cost of maintaining the system. And then if you see that what are the cost of maintaining the system in a particular time frame, like for a year, and using that you would be able to predict what will be the costs incurred for the next year and eventually after that as well. So these are some of the factors that can help in predicting the maintenance cost. Change prediction, how many changes would be required in the system? So predicting the number of change basically requires understanding the relationship between a system and its environment, as I said, and the complexity of the system. A tightly coupled system require changes whenever the requirement is changed. So tightly coupled systems are bad in terms of and that's where we try to look at the cohesion and the coupling of a system. So cohesiveness or cohesion of a system is basically the relationship within the components in a system, how the system is cohesively working together, whereas the coupling basically a tightly coupled system would basically lead to higher number of changes if the external environment changes. So the coupling, as I said, is one of the measures, and tightly coupled systems would definitely require more changes during the time frame that the system is being used. So what are the factors that influence this relationship? The number of interfaces, system interfaces it has. So the number and complexity of the system interfaces. If a system is interfaced with many different external environment components to a large scale, that means it has to communicate with many different external entities. So that means that is a complex system, and it has a large number of system interfaces. So more the number of interfaces, the more complex a system is, higher would be the number of changes that you can predict in that system. Then what are the volatile system requirements? Basically these requirements are more of like temporary system requirements, not really that you have foreseen and that are very frequently that occur. So that is also one of the barometers of looking at the number of changes the system will go through. Business processes that the system is used in. So how many number of business processes, that is again translating to the complexity of the system, cyclomatic complexity of the system. So complexity matrix is basically the prediction of maintainability of the system. So and looking at the system components, how complex they are. Normally it has been found that not all the components of the system actually require major changes. So it could be a relatively small number of system components that are frequently needed to change. So these could be made the focal points of understanding, okay, these are the the components that are normally changed, and what can be done to reduce the maintenance cost of these specific modules. So it could be possible that you might have to re-engineer those modules. That means you have to sometimes restructure them or rewrite the code for these modules to reduce your maintenance costs. So complexity of a software system depends on the complexity of the control structures, the complexity of the data structures. So as I was talking about cyclomatic complexity, which actually looks at how many decision control structures you have, how many loop structures you have, how many independent paths you have that the software follows during execution. So that actually looks at the control structures of the complexity of the control structures. Then you have the complexity of data structures. So data structures obviously can be very complex, and what different data structures do you use, which obviously would be different arrays and linked lists and some other kind of data organization that your software needs, connectivity to databases, what kind of database system it uses, whether it uses a simple database system or flat files, or it uses specific relational databases, or does it uses non-relational databases. So that could be also one of the factors to look at the data structures of it. Certain softwares obviously would be, if it is a properly defined, properly structured and designed software, would actually, and if it uses object-oriented design, then it would have objects. So you're going to look at the number of objects. You would be looking at the number of procedures or methods and the module size of that software. So this all comes together as a complexity matrix and is used to measure the complexity of a software. Then you have something called process metrics, which obviously deals with the process. So number of process metrics is basically looking at the number of requests for corrective maintenance, average time required for performing that maintenance. So also average time required for impact analysis. So that means you would basically study and analyze how this change will impact the software functioning. So how much time do you need to analyze that? Then you would be implementing that change. So how much average time is needed to implement the change? So that means that it's dealing with the software implementation now. So where you're practically changing the code or rewriting the code in some way. Then how many outstanding change requests you have. So if these things are on a constant rise, that actually is an indicator that the overall quality of the software is declining and the maintainability of the cost is increasing. Maintainability or the maintenance cost of the softwares are increasing, is going to increase in coming time. So that becomes a matrix of the quality of the software and its performance. Software reengineering basically means restructuring or rewriting either a part or the whole of a legacy system, but the functionality remains the same. So that means if you see that since you can't find certain programmers and certain modules of that or components of that software are written in a particular language, probably assembly language or probably written in COBOL now. So you may have to rewrite some parts, some components of that software, and that basically is called software reengineering. So normally software reengineering is applicable to certain subsystems, it's not to the whole system, and only certain subsystems are required which needs frequent maintenance, and these are the subsystems which may have to be re-engineered to reduce the maintenance costs. So the effort of re-engineering is to reduce the maintenance cost of the system, and as a result of that, system is sometimes restructured. That means the software code is rewritten or restructured or written in a different language, and it is redocumented. So one of the things that we see with old systems, legacy system, is that the lack of documentation is one of the major facts. So when you are obviously doing software re-engineering, probably you will be also looking at adding documentation to the software to reduce future maintenance cost of that software as well. So what are the advantages of re-engineering? The first thing, re-engineering means that you are not changing the whole software. You are only going and changing or modifying or restructuring certain components or modules of that system. So basically it results in reduced risk. So that means you're not changing the whole software, you're only changing certain parts of the software. So there is a reduced risk while you are doing software system re-engineering, which means that the risk is much less than rather changing the whole software, which demand for a big change, and rather than going for the big change, you rather go for small changes here and there. You tweak the system to make it still functional and relevant to your requirements. So there may be some as we say staffing problems and other development problems which come up, but obviously that would be, if you're changing the whole system, would actually be at a larger scale compared to just re-engineering certain components of it. Other one is in terms of cost. So software re-engineering actually reduced your costs basically. So the cost of re-engineering is often much less than the cost of developing the whole new software or replacing the whole software completely. This diagram actually depicts the whole stages of software re-engineering process, and it also explains that at what different levels and stages these changes happen. So if we see there's an original program here. So for certain components there will be a source code translation. That means you may have to translate certain source code. You have to probably understand the logic or understand the algorithm behind the source code and rewrite that into a different language. So that process is called reverse engineering. So reverse engineering is basically pertaining to analyzing the program and extracting information or the logic, the business logic behind the program, and documenting it. So basically you are trying to document the functionality of your software, functionality of a particular probably module of a software or a component of a software, and you are probably rewriting that algorithm as a pseudocode or anything to make it understandable the logic in terms of redefining the logic there. So that basically is reverse engineering. So it's basically analyzing the program itself or analyzing the component of the program. Then after that, this reverse engineering is done, there is a documentation which is created, which documents all the functionality, all the algorithm that is used, the program logic, the business logic behind the program is all documented. And after that, the program is normally modularized, which means a legacy program would have been written in a more of like a procedural manner. But if you are rewriting it, obviously you will give a proper structure to the code. Probably you are rewriting in a higher level of language, which means that you are using one of the structured languages now, or object oriented language, which obviously would provide better modularity and better structure. So program modularization happens naturally when a program is re-engineered. So that happens. So as a result of this program modularization, you are basically getting a re-engineered program. So the next step obviously is that program would be dealing with some data structures. So what data structures it is dealing with, and what kind of data it is utilizing. So then you have to go through something called data re-engineering, which means that now you have to look at the data processes that the program deals with. It might be required to study the database schemas, and sometimes modifying those database schemas to suit or rather implement them in new database environments. So it might lead to converting old databases into new database structures which are easy to maintain. It might also need a lot of cleanup of data, or redefining the data structures and redesigning the database schemas to represent the data in a more easily maintainable formats now, when supported by the new database systems. So that is part of the data re-engineering. So that happens, and then eventually you have re-engineered data. As a result of the process of your re-engineering, you also get program structure improvement. So your program structure improves overall. It might be now written into a better structured language. It might be written into object oriented approach using object oriented languages. So now obviously the functionality is further redefined by the objects, and it has been further classified into better form of structures and into better form of entities that reflect the real world scenarios, the real world examples. So overall you'll see that your program goes through a structural improvement. So now you're going to be having a program probably in a more maintainable state, because it has been written into one of the higher languages which support better structures, which support object orientation, and as a result of that the maintenance cost of that program will now be reduced, and the program's quality, overall quality, will increase in terms of dependability, in terms of performance, in terms of reducing redundancy from the code and other aspects. So now you have the restructured program, which is obviously going to be better in quality. So we discussed about that. We said a re-engineering process involves source code translation. Probably you are converting the code into a new high level language, one of those OOPS languages probably, or a better structured languages. Reverse engineering is basically analyzing the program and documenting or understanding the logic, the business rules and the business logic behind it. Program structure improvement, obviously you want to restructure the program and make it more understandable. Probably would also lead into better documentation of the program. Program modularization, obviously that means that improving the structure, overall structure of the program. Now the program is split up into probably better functions and methods, and probably using polymorphism you can have more code you can reduce the code redundancy, plus you can also improve the structure and reduce the errors, and even sometime reduce the number of code statements, because restructuring means that you are rewriting the program in a more optimal manner, in a more optimal way, and now basically that would lead to lesser code. It would generate less code, and which is easy to maintain and reduce the maintenance costs. Data re-engineering, as I said, would be restructuring the data structures and sometimes relooking at database schemas and changing the database schemas, and sometimes changing the support of database systems also and upgrading it to newer databases. So that basically would involve some data re-engineering to bring in support for newer database systems. So if a system is only required to do a source code conversion, that is step one. If the system has to also go through manual changes, that is next level of steps. And finally, if the system has to go for architectural changes, that would lead to an increased cost of the system. It also depends the initial structure of the program, initial structure of the legacy system. If it is a very system written in a typical non-structured way, in a non-object oriented way, and now effort is to try to convert that into an object oriented system, would actually inculcate very heavy costs, and sometimes may not be very wise decision to convert that into a system, into a completely new system. So it also depends on what the state of legacy system is and to what level it is the re-engineering costs. So what are the cost factors involved for re-engineering the costs? One is the quality of the software. As I said, if the quality of software is very poor, that means it has been written into really old procedural form, which is not very well structured, and now there's an effort to convert that into object oriented structure that would be very costly. What are the automated tools that are available for re-engineering this? There are certain automated tools available which probably would do the code conversion for you, but how successfully they are doing the code conversion and how much manual conversion has to be done after that, these are some of the cost factors which has to be taken into consideration. The extent of data conversion that is required, so that also has to be taken into account while looking at the re-engineering of the and the cost factors of the re-engineering of the software. So other one is the availability of the expert staff. Obviously you have to hire specialists for doing the re-engineering. So what is the availability of that expert staff? So these are some of the challenges, and these would be the determining factors for determining the cost of re-engineering. And that's typically a problem with the old systems, because these systems actually are sometimes difficult to re-engineer because of all the factors that we have discussed. One is the quality. They are written in old languages, in procedural languages. There are not many automated tools available and the support for them to re-engineer. Data conversions can be very extensive, which would need creating complete new database schemas. That would be obviously a very costly affair. Availability of the expert staff. So these are some of the cost factors that would increase the cost of engineering. The other term is refactoring. Now refactoring is different than software re-engineering, because software re-engineering probably would be looking at a major overhaul of the system functionality, which takes place after the system has been used and maintained for some time, and we see that the maintenance cost is increasing. So then you would decide that, okay, we might have to re-engineer the system or re-engineer certain components of the system. And probably you can find, if you can find some automated tools for that purpose, it would reduce your cost and decrease the time as well. But at times there may be some manual re-engineering that is done that has to be done. So that would increase the cost, overall cost of it. So if you see, the objective of re-engineering is to reduce the cost of maintenance, whereas refactoring is the process of making improvements to a program to slow down the degradation of that program, which means that refactoring is normally done via improving the code structure, and that is done throughout the development and evolution process of a software. So here the effort is to improve the quality of the code, which happens in refactoring, rather than changing the functionality, or rather rewriting big changes in the overall code. So it's basically a process of improvement of code, and it involves modifying a program, and normally this would result into an improved structure of the program, reduce the complexity, and make it easier to understand, and provide documentation for the program. Normally refactoring is done with object-oriented systems, but sometimes that same approach can be used with structural programs as well. So that also happens in structure programs. So the differentiation is that you don't add new functionality to the program, but you just concentrate on improving the programming structure. So you would be probably optimizing the code, restructuring the code to make it more maintainable, to make it more understandable, and that's what the goal of refactoring is. It's not about adding new functionality or rewriting or doing a major overhaul in the code structures, in the program structures. So as I said, re-engineering takes place only after the system has gone through some maintenance and for some time, and now the maintenance costs are increasing. So that is when the re-engineering is done, and automated tools are used for that process of re-engineering, and the goal is to create a system which is more maintainable. Refactoring, as I said, is a continuous process of improvement, and it carries out throughout the development and evolution process, and it is intended to avoid the structural errors in the code, and it is also to prevent code degradation through changes. That means you are improving the quality of the code, and trying to make it more easy to maintain. So if as a process of re-engineering, the code structure would change, and that would increase sometimes the maintenance cost. So to avoid those maintenance costs, you may have to do a refactoring, and that refactoring is done to reduce the maintenance cost of the system. Normally, when it is decided that a program needs to be re-engineered, there are something called bad spells, which basically would call for deciding that the program needs to go through certain changes. So what are these bad smells that actually call for re-engineering of the code, or eventually refactoring as well? So if there is duplicate code, so if there is a lot of code duplication in different parts of the program, that is also known as redundancy of the code, then it must be removed and it should be restructured. That is normally done to put certain repetitive code into methods and functions, and sometimes polymorphism is further used to remove the complexity of the program and to reduce the the number of code lines in the program. Certain methods which are too long could be now redesigned into short methods, so which means you have to do code optimization. Normally, if the program has too much of switch case statements, which obviously result into some code duplication, can be reduced by using polymorphic functions and achieving that functionality through polymorphism in object-oriented languages. Okay, data clumping is also, one of the reasons why re-engineering and refactoring could be brought in. So data clumps occur when certain fields and classes of a program or certain parameters are very much duplicated in a particular program. So in object-oriented programming languages, the data clumping can be reduced by using and redefining the objects which can encapsulate those data. So that is how data clumping can be removed through object-oriented approach. The other one is speculative generality, which basically means that the developer sometimes include generality in a program to add some sort of future adaptations or some future changes into it. This generality is done to make a program more adaptable and more with the scope to expand it further in the future. And some of this generality also creates extra code and extra a big software to maintain. So some generality, speculative generality, can be reduced, which is also part of optimization, to remove those code segments which are not in use or which probably would not be further extended in future. So that basically involves having a lot of abstract classes in a typical object-oriented scenario. So there may be a lot of abstract classes which are used. Now these abstract classes further are there to be extended in future, which is part of that giving a generic structure to the program that can be further extended and further used in future. So speculative generality is also sometimes has to be removed in order to optimize the program, in order to make it the line of codes to be shortened, in order to make it more maintainable. So the key points that we have discussed here is that software development and evolution are basically iterative processes, and they are integrated, and they are represented as spiral model. So basically it's an iterative process, and it happens not just once, but it happens in many different iterations, in many different instances. So we also see that the cost of software maintenance actually exceeds the cost of software development. So that is also what we have seen, and that is why there should be an effort to reduce the maintenance cost of the software. The process of software evolution is driven by request of changes and change impact analysis, and after that there's a release planning, and then there's a change implementation. So this is part of the software evolution process, and that happens in a typical software evolution process in a particular software development and evolution cyclic model. Legacy systems we have seen are the older software systems, and normally they have been developed using obsolete languages which are no longer in use, and you don't find experts programmers for those languages. At times they are using hardware technologies which are also old, and basically the challenge is to maintain these legacy systems in the current environment. It is also noted that it is at times cheaper and less risky to maintain a legacy system than to develop and replace the whole new system. But there could be a stage that arrives when you don't have any hardware support available, or you don't have any skill set available to support, to carry on maintenance of a legacy system. So a stage would come probably by analyzing different other factors that we studied, which is obviously availability of the resources, looking at the number of change requests, looking at the time frames and the maintenance costs that are involved, that we can decide whether our system has to be replaced or not. So we did something called an assessment of a business value of a legacy system, and which should be used. That assessment is used to define and to decide whether the system should be replaced, or it should be transformed, or it should be maintained. Whether it has we saw that in terms of quality and the business value. So if the quality is high and the business value is high, those systems should be continued to be maintained. And if one of these factors is missing, either the software's business value is low, or even the quality is high, then the system has to be scrapped. And if the system's business value is high and the quality is low, probably it has to be replaced with a commercial off-the-shelf system. So in terms of system maintenance, we have seen that there's bug fixing, there's modifying the software to work in a new environment, which means making it compatible to the new operating systems, and or probably implementing or changing the requirement. So re-engineering is concerned with the restructuring and of the software and redocumenting the software. So that is part of the re-engineering. Refactoring, on the other hand, is making source code changes, but the functionality is preserved. That means there is no functional changes that are applied, but only the code optimization is done, only the code restructuring is done to make it more maintainable, and it's a form of preventive maintenance. So it's basically to prevent the maintenance cost of the software. So these are some of the important